Hey guys, so today what we want to do is move on from chapter 12 to chapter 13, which is somewhat of a continuation of chapter 12. What we'll really do here is begin to combine what we learned with stoichiometry and what we learned how to do using stoichiometry with what we've learned so far about the behavior of gases. And really the ultimate focus of this chapter will be what we refer to as the ideal gas law. We'll get to that in the next video. But for today, just some background information to begin with. So just for reference, the observations we'll discuss today were made by Gay-Lussac in the early 1800s. And that's not necessarily super important that you know that, just kind of give you a frame of reference of how long ago these discoveries were made. So what happened was that Gay-Lussac noticed that as he is doing reactions with various gases, that there are relationships that exist between the volumes of gases when temperature and pressure are constant. So what I mean by that is, let's look at these two situations right here. And whatever the temperature and pressure might be, as long as they're constant, 2 liters of hydrogen reacts with 1 liter of oxygen to produce 2 liters of water vapor. Okay? So whatever units we have here, we can also say, so 2 volumes, 1 volume, 2 volumes, we could say 2 milliliters plus 1 liter produces 2 liters. So we also know to be true, if you look at this balanced reaction, that 2 hydrogens plus 1 oxygen make 2 waters. 2 moles of hydrogen plus 2 oxygens, or excuse me, plus 1 mole, let me start over, sorry. 2 moles of hydrogen plus 1 mole of oxygen produces 2 moles of water. So really what that tells us is that there's got to be some sort of relationship that exists between volume and number of moles. Because if we have these mole ratios up here, which we learned about in the stoichiometry chapter, they're also matching up with these volume ratios here. Okay, so we see the same thing here in a different example. You have 1 volume, whatever it might be, so we could say 1 liter of hydrogen plus 1 liter of chlorine produces 2 liters of hydrogen chloride, or hydrochloric acid if it's in the solution form. So up here we have it written out, 1 mole of hydrogen plus 1 mole of chlorine produces 2 moles of HCl. So again, we're seeing that these mole ratios up here also hold when it comes to the volumes of these gases. So the same thing's written out there with just a different reaction. So what he noticed was that there are small whole number ratios. That exist between these volumes. So it wasn't that 1.24567 liters of hydrogen reacted with 1 liter of oxygen. They are very nice round whole number ratios, 2 to 1, 1 to 1, 1 to 2. But he didn't really know what was going on there. But now we can use our other knowledge that we have about stoichiometry and number of moles to kind of justify what was going on there. Okay? So we can kind of further distill this down into a statement so that at a constant temperature and pressure, the volumes of reactants and products can be expressed as, again, small whole number ratios. So again, all this is telling us there's some correlation, as long as temperature and pressure is constant, between the volume of a gas and the number of moles of a gas. Sorry about that, okay? So we can write that in words. So equal volume of all gases under the same conditions of temperature and pressure contain the same number of moles. So that's a very important statement. So it doesn't matter the type of gas here. At the same temperature and pressure at a certain volume, we will have the same number of moles of gas. And we'll come back to that in a moment and actually look at that mathematically. So we talked about in the previous chapter, Boyle's law, Charles' law, Gay-Lussac's law, all these ratios that exist between the different variables that affect gas. And you might have noticed that the one that we didn't discuss was number of moles. So we need to look at the proportion that kind of correlates number of moles with the other variables here. So we'll call this Avogadro's law. Okay, so he proved that a direct relationship exists between the volume and number of moles of a gas. So now we have Boyle's law, Charles' law, Gay-Lussac's law, and now Avogadro's law. So we have that volume divided by number of moles is constant, so that is a direct proportion. Okay, so as volume increases, so will the number of moles. As the number of moles increases, so will the volume, as long as pressure and temperature are constant there. Okay? So we can see the same thing written down here below. If you have this reaction, H2 plus HCl produces 2HCl. So we can say it in terms of, as long as we're at constant pressure and temperature, I can say at constant P and T, this is true. 1 liter plus 1 liter makes 2 liters. But then the second two lines here are the same thing, but they don't require constant pressure and temperature. It's always 1 mole reacts with 1 mole to make 2 moles. And 1 molecule reacts with 1 molecule to make 2 molecules. Okay, so it shows us there's a correlation between moles, molecules, and volume as long as temperature and pressure is constant. So if you look at these ratios, that also kind of confirms and helps support, if you look back up here, the existence of diatomic gases. Okay, so this ratio supports the existence of diatomic molecules due to the charges. Sorry about that, a student walked in, so let me kind of start that over. If we didn't have, or if certain gases weren't diatomic, to produce water, it would be logical that we would need 2 hydrogens, 1 oxygen to produce H2O. Okay, so we can kind of see that supported there, but there are other situations where that wouldn't work out. Okay, so the ratios that we have here show that in some situations we have 2 gas atoms, I guess, present in the same number of moles of the gas, versus some situations, something like neon, you might only have 1 mole of atoms, okay, present there. So we already know this, hopefully we've looked at before. The diatomic gases are hydrogen, nitrogen, oxygen, fluorine, chlorine, and then bromine and iodine. Bromine's a liquid at room temperature and iodine's a solid at room temperature. So those are the typical diatomic gases we deal with. And then the noble gases, or the other gases we typically encounter, those are not diatomic. Okay? So don't worry so much about the logic behind that. Just know that's kind of where the whole original rationale for diatomic atoms and gas molecules came from. Okay, so now we really say all that just to say this. We now know that what we call the standard molar volume of a gas, okay? So that is basically just a new conversion factor that we have that at STP, so remember STP, hopefully you remember, is 0 degrees Celsius and 1 atm, or some pressure unit that's equivalent to 1 atm, or some temperature that's equivalent to 0 degrees Celsius, so it could be 237 Kelvin, for example. We know that at that temperature, 1 mole of gas occupies 22.4 liters of space. And that is completely independent of the type of gas. So you have an example down here where you have a sample of hydrogen and oxygen gas. So you have 1 mole of hydrogen, 1 mole of hydrogen, 1 mole of oxygen. They both, if they're at STP, they both occupy 22.4 liters of volume. They both have the same number of molecules because moles and molecules are equivalent there, or not equivalent, but they're used to determine each other. But the masses are very different, okay? So there is no mass here. So make sure you're aware of that. There is no correlation between volume and mass, but it's worth writing this out again. So at STP, 22.4 liters of any gas equals 1 mole of that gas. And that is very important that it's at STP. If it's not STP, that does not hold, okay? So you can look through this kind of chart and think about what this means to yourself. So in the past, when we were doing stoichiometry, all the problems started off something like I have 12 grams of magnesium or 13 grams of iron, whatever it might be. And then the first step was always to convert from grams to moles because we had to have our number in moles to use our mole ratio. But now hopefully you see, if we're dealing with gases, we don't have to know the mass. We can start off with the volume of that gas. And as long as that gas is at standard temperature and pressure, 0 degrees Celsius, 1 atmosphere, we can convert from liters to moles of that gas. So we can cut out the mass step, because we don't use the mass in the stoichiometry calculations. We use mass as a means to obtain the number of moles. Okay, so hopefully you see how important that can be when we move forward, because it's much easier to measure the volume of a gas than it will be to measure the mass of a gas there. Okay, so I'm going to stop this video here. Then in the next video we'll kind of start to apply this. So this is something you got to memorize. Okay, so commit that to memory. 22.4 liters of gas is equal to 1 mole. So if you're an in-person student, you're likely in my classroom. Upside down. I've seen this little box before. If you're not in person, here it is. It's just a little representation of what 1 mole of gas looks like. Okay, so this little box would be 22.4 liters. Okay, so 1 mole of any gas would occupy the volume of this box. But inside the classroom it wouldn't, because the classroom is not at 0 degrees Celsius. So if the pressure of the gas was 1 atm and the temperature of the gas was 0 degrees Celsius, all of these gases would have these masses, but their volume would be equal to 22.4 liters in the size of this box. So in the next video we'll kind of apply this calculation to solve some problems.